I think we will have to start if we want to go through it. So, hello everybody, welcome to this last session of the webinar about role of ventilation in infection control. So we will have 7 presentations this afternoon. I'm Valérie Leprince from CEREMA, and I will be chairing this session with Professor U.Yanagi from Kogakuin University, more or less, sorry, School of Architecture. And the first presentation will be his presentation on aerosol transmission route of respiratory pathogen and their mitigation strategies.
Thank you for your introduction. I'm very honored to be here, to be able to give a talk here. My presentation, the title for my presentation is Aerosol Transmission of Respiratory Pathogens and Their Mitigation Strategies. Okay. And today, I would like to talk about 3 topics: transmission route of infection respiratory passengers, physical and biological characteristics of SARS-CoV-2 in the air, primary engineering mitigation and strategies for respiratory infections. The first topic is the transmission route of infectious respiratory passengers. And this slide shows the traditional definition of transmission route and the recommended distance to avoid infections. The mode of transmission of respiratory infections have been classified contact, droplet, and airborne. And WHO defines respiratory aerosols with a particle size of larger than 5 micrometer as droplets, and dried respiratory aerosols with particle size smaller than 5 micrometer as droplet nuclei. And droplet and airborne infections are defined by droplet transmission and droplet nuclear transmission or airborne transmission and respiratory. And regarding the recommended distance to avoid infection varies from 1 meter for WHO and in parts of Europe to 1.5 meter in Australia to 2 meter in the USA, Canada, and the UK. And the classifying of droplet infections and airborne infections with 5 micrometer as the threshold diameter is a dualistic medical dogma that has not been proven by direct measurements. And in fact, larger than 5 micrometers of SARS-CoV-2 has been detected in the air. The WHO emphatically declared on March 28, 2020, that SARS-CoV-2 was not airborne. In July 2020, WHO conditionally admitted aerosol transmission. In December 2021, WHO clearly stated that aerosol transmission or airborne transmission for the first time, it takes 2 years. Currently, there is no public consensus on the term of transmission route. And this slide shows the one suggestion. Instead of traditional definition, this paper suggested inhalation of aerosols, spray of larger droplets, and touching a contaminated surface. The second topic is the physical and biological characteristics of SARS-CoV-2 in the air. This slide shows the definition of aerosols and bioaerosols. Aerosols is a suspension of solid and liquid particles in a gas. The term aerosol includes both the particles and the suspending gas, which is usually the air. The particle size range from 0.1 nanometer to 100 micrometer. And biological particles size may range from aerodynamic diameter of circa 0.5 to 100 micrometer. Since the SARS-CoV-2 is released from the mouth with the air, so it is in the state of aerosols in environment. And this figure, the upper figure shows the terminal setting velocity and the time to set 1.5 meter in still air. For example, the setting velocity of a 10 micrometer particle is 0.003 meter per second. So it takes about 9 minutes for least to fall from a height of 1.5 meter to the floor. And the airflow velocity in a mechanical ventilated rooms is several tens times higher than that setting velocity. So therefore, while the particles are falling, they are carried far by the room airflow. And these figures by river shows the traveling distance estimated of different size of droplet to be carried by room air velocities of 0.05 meter per second and 0.2 meter per second. And this, the upper figure shows the respiratory systems and the deposition characteristics of aerosol particles in the respiratory system. The figure below shows the aerosol released from the human respiratory systems changed in the environment. The released droplets contain virus, proteins, salts, water. Aerosol particles from various sizes due to the water evaporation. Some studies show that after water evaporation, the particle size shrink to 25 to 50% of the initial particle size. In addition, the indoor temperature and the relative humidity, UV lights, affect the activity of virus. The first way to prevent a virus in the indoor environment is to wear a mask. This doesn't cost money. But this cannot completely prevent the virus, as engineering countermeasures against the virus suspended in the room, controlling temperature and relative humidity, increasing ventilation rate, using a high collection efficiency air filter using UV rays are effective strategies. Initially, it was believed that the transmission route of COVID-19 was only by the contact and droplets. However, now, COVID pandemic has showed that airborne transmission is a major mode of transmission of this disease. My presentation today will talk about mitigation strategies by ventilation, filtration, and UV sterilization. Next topic is the primary engineering mitigation strategies for respiratory infections. Infectious disease occurs when three elements that are infectious agents, susceptible persons, and transmission routes overlap. And a susceptible person is exposed to an amount of passenger that exceeds the threshold of dose response relationship. Engineering mitigation strategies for respiratory infections are basically transmission route measures. It is to keep occupants exposed to the virus below the threshold. And this slide shows the mitigation strategies for respiratory infections by transmission route. The transmission models of respiratory disease can be classified into 3 types: contact, droplets, and aerosol. Maybe this is traditional definition. Contact transmission countermeasures are mainly hand hygiene and surface cleaning. The main countermeasures for droplet transmissions are avoid 3 C's: wearing a mask, ensuring social distancing. Regarding the aerosol transmission, behavior change is important first, and we have 3 ways of engineering measures: ventilation, air purification, and UV sterilization. Regarding the ventilation, before talking about ventilation strategies, I would like to explain concept of the equivalent ventilation rate. If the air contains particles contaminants, a part of contaminants will filter as it passes through the filter. And this formula shows the mass balance. The amount of pollutant in the upstream side of a filter is item 1. The amount of contaminants filtered by filter is item 2. And the amount of pollutants in downstream side of the filter is item 3. In case of coloration efficiency of air filter is 19%, and assuming that the amount of the polluted air on the upstream side of the filter is 100. So 90% of the air will be clean air after passing through the air filter. And this amount of clean air is called equivalent ventilation rate, or equivalent air, and clean air. And this slide shows an overview of an office which with a central air conditioning system that is a typical system in Japan. And this slide summarizes some engineering mitigation, ventilation, UV. And the law for environment health in buildings of Japan sets a standard of 1,000 ppm for indoor carbon dioxide. So about 30 cubic meters per hour per person required to meet this standard. This ventilation rate corresponds to approximately 2 air change per hour. In Japanese office buildings, one person occupy average 5 square meter. However, the temperature and the humidity cannot be adjusted for the ventilation rate only under 2 air changes per hour. 2 to 3 times as much air volume is needed. In order to save energy, we usually reintroduce the return air, assuming that the return air is 2 times the amount of outdoor air, and the air purification coloration efficiency is 90%. So the equivalent air change per hour will be 5.6. It is well known that increased ventilation rate can reduce the risk of infection. This figure shows the difference of infection probability between case B with 2 air changes per hour and the case A with 5.6 air changes per hour includes equivalent ventilation. By the way, increased ventilation rate can shorten the virus staying time indoors. As a result, it can reduce the risk of infections. Regarding the ventilation rate for mitigation aerosol transmission, in the earlier 20th centuries, buildings proposed and actually recommended outdoor airflow rate for 51 cubic meter per hour per person based on the consideration of infection prevention. And then systematic reviews of research on the quantitative relationship between risk of infections and the ventilation rate have concluded that sufficient data to specify minimum ventilation rate for infection control does not exist. And this review was by Professor Yuko Lee. And the WHO recommended the minimum outdoor airflow rate of 36 cubic meter per hour per person for the non-scale facilities and 216 cubic meters per hour per person for the most space in healthcare facilities. And recently, several suggestions have been made for air changes per hour. The Lancet COVID-19 Commission Task Force on Safe School, Safe Work, and Safe Travel breaks down air delivery rates and NADR into three categories for airborne respiratory disease. The good category corresponds to the ventilation rate is 36 cubic meter per hour per person, and this is same as the WHO's recommendation for the non-healthcare facilities. And the better is 50 cubic meter per hour per person, and this is the same as the billings recommended in earlier 20th century. And the best is larger than 50 cubic meter per hour per person. And regarding the central and filtration, an air filter collects suspended particles near the filter medium and by a mechanism such as an initial collection, interception, diffusion, and electrostatic attraction. In fact, particle collecting by an air filter is based on one or more of these mechanisms. The mechanisms differ depending on the particle size. The coloration efficiency increase with the internal with the initial impaction of large particles and with diffusion of small particles. It is lowest for particles when an approximately of size of 0.2 to 0.3 micrometer. And this table shows the minimum efficiency reporting various MAV and the filter efficiency by particle size. The colorimetric method was used for the existing filter in Japan. And this part filled with colors shows the collection efficiency of filters that are often used in Japanese office building. According to the measurement date of this paper, when using MOV 12 or 13, MOV 13 filter, the single pass of collection efficiency is about 85 to 88%. The medium performance filter is very efficiency. The last topic is GUV. Microbial response to GUV exposure can be modeled as a single stage exponential decay or two-stage exponential decay, and the response may include shield. The bactericidal effect of UV rays is related to the irradiation intensity and exposure time. The stronger the irradiation intensity or the longer the exposure time, the higher the bactericidal effect. Therefore, it is easy to use UV light on the surface sterilization where longer exposure time is easily to be obtained. On the other hand, since the exposure time in the space is short, it is necessary to devise ways to increase the irradiation intensity or lengthen the exposure time. There are two types of UV sterilization, the upper room method and the inductor method. Upper room method and inductor method. And this slide shows an example by CDC of an upper room GUV. The first major premise is not to expose the occupants directly to the UV rays. The virus rise up part of the room by the updraft due to human body heat and then sterilized by UV. This Gemma's viewpoint indicates that upper room GUV air disinfection, commercially available upper room GUV in air disinfection has been shown in clinical settings to reduce airborne tuberculosis, TB, transmission by 80%, equivalent to aiding 24 rooms air changed per hour. It's beyond my imagination. This Lancet paper describes the effectiveness of surface sterilization in the inductor light. Currently, a lot of data on impact of UV on coronavirus has been reported. Summary. And the main engineering mitigation strategies for respiratory infections is control exposure load below the threshold, that is lowering the concentration for viable virus indoors. Dilution by ventilation. Increasing the dilution rate also means can shorten exposure time to the virus. Removal by filtration and or increase equivalent air change per hour. Sterilization by UV rays. And these are posters about influenza measures published by Japanese government 100 years ago. Wearing a mask and disinfecting with sunlight was recommended. Thank you for your attention.
Thank you, Professor U.Yanagi. Do we have any questions? We do have time for some questions. Yes, Pavel.
Well, thank you very much for the interesting presentation. Has anyone in Japan made estimation by comparing the mask efficiency versus technical solutions, saying if you wear a mask, you will not have to, for example, install that much ventilation, or you will not have to use UVGI, or you would not have to use the filtration. So basically comparing the effect of mask wearing against the technical solution. Has anyone done this estimation in Japan?
You mean comparing with wear mask and not? In my, I don't investigate the case between the you say the two cases. In fact, it is well known that the mask is very effective, but in Japan, maybe not in Europe. Thank you for your comment.
Yes, another question. We have the microphone here.
Thank you. I know some experimental work made by Tokyo universities to use COVID-19 virus itself. And in the chamber box, there is a dummy head located. Emit droplet, including COVID-19 virus. And on the other part is induce the air. And the result shows that the mask has, especially the surgical mask, has effect of reduction of 50% for emitting and 20% reduction by accumulating. So the multiplier of these is effect of mask. So if appropriately one mask has very effective to decrease risk of infection, I think. Thank you.
Thank you very much. Is there another question there?
I'm Kazukumagai, working for California Department of Public Health. At my department, we've done.
What's the microphone?
Another mic. In my department, we did that kind of a comparison, the efficient comparing when you have mask and not mask, and how would the ventilation work. So I can share the document, the link to the document later.
Thank you.
Thank you very much. One last question. So I think we can thank you, Professor Yanagi. And